I'm certain that something I say will be something that I don't necessarily want on the recording, but I can't control that. All right, we're going to talk about sorting arrays. It's pretty straightforward. We've got the arrays concept down. It's just a list of values. That's all it is. Now we can sort these values as long as they're numerical or alphabetical, but we're going to focus on numerical for today. Let me get this out of the way. So we're going to talk primarily about the bubble and selection sort. Now look, I made this in 2023. We did talk about, we watched this video of all these different sorting algorithms, and there are hundreds, and people write new sorting algorithms all the time. The goal is to try to make them faster. Some algorithms are better at certain types of data, but the idea is all of them organize the data. That's all they're for. Some of them are faster, some of them are slower, but they all just organize data. So we're going to go over and talk just about these sorting algorithms. When we talked about before, we talked about algorithms. This is just a step-by-step process that does a thing, right? So whenever somebody uses the word algorithm, it sounds fancy, but all it is a step-by-step something that does a thing. That's it. What our sorting algorithms do is they look at an array and they look at it and go through it over and over and over again. And every time they go through it, they can only move one or two different values, right? They can't do a whole lot every time they go through it. But if they can go through it over and over and over and over and over again, then eventually they can sort the objects or sort the values. So a bubble sort compares adjacent elements and swaps them if they're in the wrong order. So this is the one that we kind of looked at last week, where it's going to look at element 0 and compare it to element 1. If element 0 is bigger than element 1, it's going to store it in a temporary variable and then swap them. And that's all it does, is it just swaps two elements and then looks at the next two elements. A selection sort looks at every element in the array and finds the lowest number. It puts that number at the very beginning. And then it looks through every number in the array and finds the second smallest number, puts that number in the second slot. Looks at every single number in the array and finds the third smallest number and puts it in the third slot. Make sense? It goes through pretty quickly. These both end up with the exact same result, right? They both end up with an array that is sorted from smallest to largest, but they do it differently. And this is a good example in programming. Just like in math, there's almost never one right answer, right? If you want to do something, you can accomplish that task any number of different ways. Sometimes it'll be bubble sort, sometimes it'll be a selection sort, sometimes your way might not be the fastest way, right? But certainly for the purpose of this class, we're just worried about getting it done. Eventually, if you were programming for the Department of Defense, they would want you to do it the fastest way, right? But there's two levels of fast, right? You can say, I can program this in a day and a half and get it to you, but it's going to take 6 hours to run. Or I can program this in 3 months and get it to you and it'll run in 15 minutes, right? There's always a balance when it comes to coding as to how efficient it is versus how quickly you can get it done. And this is true in gaming as well. And you will see that every game you play today probably has a glitch in it somewhere. There will be a glitch that someone finds. The reason for this is because they're not exactly worried about the code being perfect. They're worried about the code being shipped. If you can get it out the door, then you make more money, even if there's a couple of mistakes. But this happens even in every software that we get, right? So you've probably had some issues at some point with logging into something, right? Like it forgets your password or it just locks you out for some reason, for no reason. You click on a link and the link doesn't work, right? This is because we are worried most of the time about getting things to market rather than getting things done perfectly. And this is a symptom maybe of having compilers, because we hit the run button and it compiles and tells us if everything is working, right? When we had to program things on punch cards and you had to punch in all of the individual elements, binary code, and then you had to run it through a machine, but you had to reserve the time on that machine 2 weeks in advance. Then you really needed to make sure that your punch card was not incorrect, right? And we took that and went to the moon, right? Because we didn't make mistakes. Now we make a lot of mistakes, but we're faster at it. So you kind of decide what the goal is, right? And in most companies, the goal is getting it shipped. So we're not as worried about efficiency as we used to be in the world of computer science. We're worried about how quickly you can get it out the door. But we'll look at creating a timer as well, so that we can time how long it takes our code to run, because the goal is to make it faster. But that's just for fun, really, because no one cares. So here's an example of a bubble sort. The array is 42153. The very first time it runs through the bubble sort in the array, it ends up with 21435. What happens is it compares the 4 to the 2 and it switches them. It compares the 4 to the 1 and it switches them. It compares the 4 to the 5 and it does not switch them. And then it compares the 5 to the 3 and it switches them. So this is how you end up with 21435, right? That's the first iteration. The second iteration it goes through, it compares the 2 to the 1 and swaps them. It compares the 2 to the 4 and does not swap them. It compares the 4 to the 3 and swaps them. It doesn't have to compare the 4 to the 5 because it already knows that the 5 is the highest value because it went through the iteration once. That's what a bubble sort does. Step by step, 2 numbers at a time, and swaps them if they're in the wrong order. So here's what we call pseudocode for a bubble sort. Now, pseudocode is not actual code. It's never actual code. This is generally written as close to English as you need it to be written so that you can get it down on paper quickly. Some people's pseudocode looks a lot like code. Some people's pseudocode looks a lot like English, right? It doesn't matter where you are or what your pseudocode looks like. The idea is you want to get your ideas down on paper as quickly as possible. And don't worry about the actual syntax of it. So, making a for loop from I to n minus 1, where n is the number of elements in the array. So if you have 10 elements, then this is going to be 10 minus 1, or 9. And then the J loop is n minus I minus 1. What this does is it allows the bubble sort to go through the iteration the second time to ignore the top slot. Because remember, we assume that the top slot is correct after the first iteration. And we continue that loop. And as long as array J is greater than array J plus 1, we swap them. This is pseudocode. It's not real code. But this is the idea of what we want to do. So now we're going to talk about the selection sort. We have the same array, right? The first iteration, well, the array is 42153. You'll notice we have a lot more iterations here to get through, right? This means that for this particular set of code, or set of values, the selection sort feels like it might be slower, right? We have a lot more iterations, but let's look. First iteration, we find the 1 and we move the 1 to the front of the line. Now, I don't know why I swapped the 2 and the 4 here. Oh, I do know. We don't just move the 1 to the front of the line. We swap the 1 with the element in the very beginning, right? So right now the 0 slot is a 4, but a 1 is in the 2 slot, 0, 1, 2. After we look through the array, we find that the 1 is the lowest number. We swap the 1 with the 4. Then we look through the array again. We find that 2 is the lowest number. The only thing we could do is swap the 2 with itself, which we don't have to do, right? So we don't. The second iteration, or the third iteration, we look through and we find the 3. We swap the 3 and the 4. And then the last iteration, we find the 4. So we swap the 4 and the 5. And then we know that everything is in place. This feels slower than the bubble sort, right? And in some instances, it will be. But instead of coming through and making a swap and then a swap and then a swap, this is making fewer swaps. So maybe it's faster, right? Even though it's going through more iteration, it's actually doing less process. Depends on the type of array that you have. So the pseudocode for a selection sort. Again, from I to n minus 1. And then we set the minimum index equal to I. So in this case, the minimum index is 0. Now, this isn't a great example. This should be negative 1,000, right? Your minimum index has to be lower than the lowest value that you have in your array. And this is hard sometimes because you haven't looked at your array yet with the code, right? So you don't know what the minimum index is going to be. If it's an array of only positive numbers, then 0 works as your minimum index, right? But if it's an array where it can have some negative numbers, then do you need to go to negative 100 or negative 500? There's some sort of projection guessing that you have to do when you write a code. And this is why a lot of times there is a glitch, right? Because if I write a program to sort, but my minimum index is 0 because I'm assuming all the values are positive, and then somebody tries to run my code on something with negative numbers, it's not going to sort them. So we do the best we can, I guess, right? There's always a balance between the time it takes and how good it's going to be. So hopefully you write it good enough to work with everything, but it depends. And really you should know a little bit about the data set. Like if I'm sorting your grades, right? I know that the lowest grade has to be a 0 and the highest grade can't be more than 100. I know that about the data. When you're programming anything dealing with data, you have to know something about the data before you start, or you're going to give yourself some gaps. So you set the minimum value to I. In this case, it's 0. For j equal to I plus 1, for j starting at I plus 1 going up to n, where n is the number that you have. So if you have 10 slots, you start at 1 and you go all the way up to 10. It looks at the j slot, which in this case starts at 1, and compares it to the minimum index. If j is less than the minimum index, then it's going to change the minimum index. And at the very end of the loop, it's swapping the minimum index and the first slot in the array. So if the 5th slot is the lowest number, then it's going to swap it with the first slot. And this is the pseudocode that accomplishes that.
And after that point, it doesn't matter what your original minimum index was.
Right, because your minimum index has been updated. Yeah. But this can create a problem sometimes if you have a whole lot of values with the same number, right? Because then it's not less than, you would need to change it to less than or equal to if you were going to have that issue, right? If you have all unique values, then less than works. But if you have a bunch of values that could be the same, then it's got to be less than or equal to. So bubble sort is probably the easiest to program, right? It's the fastest, it's easiest. It works well on small arrays and arrays that are nearly sorted. If you have an array of 50,000 slots, it's going to take forever for the bubble sort to get through it, but it will work. It will get through it, but it will just take a long time. And sometimes that's okay, right? But generally, we consider it not to be suitable for large arrays because it is just slow. And it's certainly, if it's completely unsorted, then it's really, really slow because it's doing a lot of processes where it's swapping numbers, right? If it's close to sorted, then it's not swapping as many numbers, so it's a little bit faster. But either way, if it's not sorted at all, the bubble sort just takes a really long time. The selection sort is also really easy to write compared to other sorting mechanisms. It's a little bit more difficult than the bubble sort to write, but it works really well on small arrays. It is not suitable for large arrays either because of the fact that it's doing one at a time and it just takes a long time because it's making a ton of individual comparisons. But these are the two we're going to learn because these are the easiest ones, right? We can look at other ideas later, but we only have an hour today. So what we've done, we've talked about the bubble sort and the selection sort. We've looked at the pseudocode. I'm going to go through a demonstration. We're going to write this code for the bubble sort. We're going to come back and we're going to write this code for the pseudo sort. And then we're going to populate a couple of arrays and see how they sort through. And then we will use these concepts to talk about parallel arrays and sorting parallel arrays. So when do you use a bubble sort? Anytime you're sorting a small array or nearly sorted array. This is really good as educational purposes, right? The bubble sort was great when somebody decided to use it, right? As a first easy algorithm, they're like, oh, this will definitely work. And it does. It definitely works, but it just takes forever. When the array is small and the number of elements is already known and not likely to grow. In some instances, if you used a sorting algorithm that you wrote and you used it to test an array of 10 slots, right? And it works really well. But over the course of the next 2 years, if you add something to that slot every couple of weeks, and you might add 5 units or you might add 15 units, then eventually, by the time you get to the end, it might take 2 hours to run your bubble sort, right? So knowing how the data is going to be used and knowing how the data is going to be added to or improved or modified over time. So this is something, think about you're making a game and you have a high score table, right? If your high score table only has 10 possible slots, but a bubble sort works really well, right? Because it takes the new score, compares them against the slots. Actually, you probably use an insertion sort, but whatever. And compare it against the slots, and it'd plug it in, and that would wipe out the last slot, right? But if your high score table was never getting rid of any scores, right? It was just keeping every single score that ever happened. Then after that game had been running for 2 years, 3 years, then the sorting algorithm is going to take forever, right? So understanding how your data is going to be used. The bubble sort is not a very good sort, but it's easy to learn and it represents the concept. Selection sort is similar. It's really good for small arrays. And sometimes if you just need something that's effective but quick to write, the selection sort is going to be good. If you're using like a really old machine, right, that has really low RAM, the selection sort, even the bubble sort, would be really good because it doesn't have to save a whole lot of information while it's running, right? So it is not going to overload your memory. But the selection sort is used most of the time as a element of more complex sorting algorithms. Something that's going to do a lot more intense sorting will start with like a selection sort on like 10 units, even if it has 1,500. And it'll figure out those 10 units and then remember those 10 units and apply it as they go through. So I think one of the videos you saw it sorted like a chunk and then another chunk and then another chunk and then another chunk and then another chunk. So it's sorting chunks of 10, but it's remembering all of the elements in those chunks so that it can just put them together in the end. We're not doing that, but that's an application. All right. So that is the sorting algorithms that we're going to do. What are your questions about sorting as far as arrays are concerned? I did. I guess I don't see it. But it's in there. So one of us is falling down on the job. I'm going to pause my recording. All right. So we have the bubble sort. It's pretty straightforward. What we have to do is Brooks wants to know the largest possible array we can make. In the CPP shell, it's actually smaller. The CPP shell doesn't have as much memory capacity as your computer does. It works really well for this educational aspect of teaching, but if we were trying to process really large data sets, we wouldn't be able to do it. But we're not. So we're going to make an array. Let's just say we're going to start with 10 units or 10 slots. So int, we'll call it my array 10. And then in order to populate an array, so I'll use some quotes here. So this is declaring an array of 10 slots. To populate an array, we use a for loop. Yeah, use a for loop. But before we can do that, we have to create the random values, right? So we need srand time.h, no, time 0, srand time 0. Right, that gives us a random seed. Is that right? Or does this need to be something different than 0? I think it needs to be 0. Let's find out. So I'm in a random variable somewhere between 0 and 500. I'm going to output that variable. I just want to make sure that my random time is correct. And it is. I get a different number every time I run it. All right, so we need to populate our array. In order to do that, we're going to use a for loop. So for int I starting at 0, where I is less than 10, I plus plus. Now, we know that our array is 10 units. So we can have a for loop that runs in 10 units. This is for populating, right? If we had a length of an array and we didn't know how long that array is, then we could use this. I think we looked at last class doing length of, and it didn't work. But there is a way to access the actual length of the array and use it in this slot. We don't have to do that because we know the length of the array, and mostly because it didn't work and I don't want to, because I haven't figured out why it didn't work yet. Transparency. So we have to populate the array. So in order to do that, we're going to do my array I equals some random value. So rand percent. We have 10 slots. What do we want the random values to be between? If we use 0 and 5, we're going to get a lot of doubles. If we use 0 and 1,000, we're probably not going to get any doubles. We use 0 and 10, we might get some doubles, but we may not. What do we want? 0 to 100? We'll just put a 100 there. Probably won't get any doubles, but it could happen, right? So we'll see what that looks like. So this is going to give us an array. And this array is going to have random values in it. And if we want to see what it looks like, we can print out my array I, and then just put a colon in between them, and that'll print out all 10 of our array slots. So we have a 91, a 50, a 39, a 1, a 66, a 30, a 62, an 85, and two 84s. Look at that. Doesn't matter because we're not sorting them right now, but we did get some values that were the same. So if we were to sort this with a bubble sort, the first thing that would happen is it would compare the 91 and the 50, and it would swap them because 91 is too big. It would compare the 91 now and the 39, and it would swap them because the 91 is too big. It would continue that, swapping the 91 until it got all the way to the end. The first version would look like 50, 39, 1, 66, 30, 62, 85, 84, 84, 91. And then the second loop would start over comparing the 50 to the 39, and it would take it a couple of steps. So what we want to do is visibly represent what's happening, right? So this is the very first version of the array. But now we need to sort it. So we're going to actually create the bubble sort function. Loops. Not the bubby sort, bubble sort. So we talked about a bubble sort has to be a nested for loop, right? So the first loop is for int I, where I is less than 9, right? Because we take the number of slots in the array minus 1. So in this case, it's 9, because 10 minus 1 is 9, and then I plus plus. And then we have a nested for loop, where j starts at 0, and j is less than 9 minus I. Now this 9 minus I, the first time it goes through the loop, I is equal to 0. So it's going to go through every single element in the array and compare it to the element above it. The second time it runs through, I is going to be 1, so it's going to go through every single element in the array except for the last one and compare it to the element above it. So forth and so on, right? So all we're doing here is looking at if my array I is greater than my array I plus 1. When it is greater than my array I plus 1, we want to swap elements. In order to swap the elements, we talked last class, we're going to make a temporary integer and set it equal to my array I. Whoa. We're going to set my array I equal to my array I plus 1. And then we are going to set my array I plus 1 equal to temp. So these three lines swap the elements. In the event that my array I is not greater than my array I plus 1, then it's going to skip over this and it's not going to do anything. Right? Now, at the end of this iteration, right here, right, we want to, for the sake of demonstration, we want to draw our array, right, so that we can see. So drawing the array, it has to be inside of a for loop, and we have to draw each element of the array. So this will be the first time we've nested two for loops inside of a single for loop. So one of the struggles, one of the frustrating parts of dealing with arrays is you can't ever look at an array unless you stick it inside of a for loop. There's no way to just print out the array, because what it does when you do a see out of an array is it gives you the memory location of that array. You can't see out it without looking at all the individual elements. So sometimes, I mean, if you have 10,000 elements, then this is going to take a really long time. But usually you're not printing out 10,000 elements. We have 10, so it should work. So every time it goes through this loop and it swaps them, it should give us the full array. So let's see what happens. Nothing happens. Why is nothing happening? I'm going to let it run for a minute. My problem in my code, for those of you that are keeping up in the video, is in this loop, the J loop, I had I is less than 9 minus I. And no matter how many times I went through the loop, I is always going to be less than 9 minus I. Sick, because that's how numbers work, right? So I had an infinite loop, which was a logic error, but now it is fixed thanks to the watchful eyes of my students. And when I run it, I get just a list of arrays, right? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different versions of my array. So the first time I go through my array, I compare 78 to 14 and swap them. Next time I compare 17 to 28 and I swap them. Next time I compare 78 to 33 and I swap them. 78 to 13, I swap them until 78 goes all the way to the end. Now this is just one cycle, right? Because everything's not in order. But after one cycle, I've successfully moved the 78 all the way to the end of the array because it was the biggest number. So now we would need to go through that whole cycle again. And I really thought that that's what this would do. So this is going to sort inside of this loop. And copy this out. Put it down here. Delete it.
No, I think it's doing it. It's just you limited it to 10 cycles in your.
Aha! Thank you. No, it shouldn't matter because then it's going to run it again, right?
Yeah, but they're only printing it.
Because when I is 0, then it's going to run this whole loop. And then when I is 1, it's going to run the whole loop again, theoretically. But it didn't. But it should have. Same thing. My second error was I was comparing my array I to my array I plus 1, which meant no matter how many times I went through my J array, I just did that same thing 10 times because I never changed while I was in my J array. So inside the J loop, I need to change it all to J plus 1. Now let's see what happens. So much better. So now I have a fully sorted array. So if I take this for loop, I'm going to put it back into here. 2 nested for loops inside of 1 for loop to make another end line. Perfect. So the first time it goes through the iteration, it moves the 96 to the end. Second time it goes through the iteration, it finds the 84 and it moves that to the end. Third time it goes through the iteration, it finds an 83 and it moves that to the end. 82 moves it to the end. 81 moves it to the end. 63, 61, and eventually it's 5, 6, and everything is in order. What's really cool here is everything gets into order here, right? Because the 5 is actually less than the 6. Sometimes it is possible that your code could get everything in order up here, right? The way that the bubble sort works is it still has to make all of these comparisons, which is another reason the bubble sort is not super efficient, right? Because it doesn't necessarily know when things are in order. It just knows when it's gone through and made all the comparisons. So run it again. And no matter how many times you run it, look, we did it again. So this one was correct here, then it still had to run the extra 2. So if you had 10,000 numbers, then you might want to put an extra check in that says if all of these are in order, don't do it again. But the way we're doing it here is just a little bit slower. So that is a bubble sort.
Question: When you get to the final arrangement being correct,
Yes.
then it's still theoretically faster because you don't have to do a
Yes.
bunch of swaps.
Right.
So you're not using computing.
Yeah, so it's skipping, once everything is correct, it's skipping these what's that, 6 lines of code, right? Those don't happen, which makes it a little bit faster. Yeah. But it's still doing this check. It's just not doing this effort, I guess, this swap. So I want you to see it all, but there's not. Well, I guess the only thing you really need is right here, right? So this is the bubble sort itself. Everything else is just drawing the array or populating the array. So I'm going to pause the recording. Everybody sitting here will get to hear this twice. So I've gone through and I've made a print out, which gives me a delineation between my bubble sort, which is all of this, and my selection sort, which is going to come next. In my selection sort era, I'm going to repopulate my array with new random values. Once it's populated, all I'm doing is finding the smallest value in the array. I'm creating a variable to hold my small, which will hold the smallest value. And then I'm creating a variable to hold my slot, which is going to tell me at what slot the smallest value is. So in order to do that, I have this for loop. And this for loop looks through, compares all my values against my smallest value. And if my current value is smaller than my smallest value, I'm going to reset my smallest value and my small slot to I. Once I've gone through the whole loop, I'm just going to do a cout so that we know what my small is, and so we know what slot it's in. So I have my bubble sort. It works. I have my selection sort. Interestingly enough, the smallest number is the first number, 2, which is in the 0 slot. I'm going to run that again. I don't want it to be 2 in the slot. So the smallest number is 4 as it goes through, and it is in the 5th slot. 0, 1, 2, 3, 4, 5. So now what I can do, because I know where the smallest number is, I can swap it with any other number in my array. The easiest thing to do is to swap it with the very first number because I want the smallest number to be the first number. So once I'm done with this for loop here, then I want to swap the smallest value with the first value. We should be familiar with how to swap values, right? So my array, we got to make a temp. A temporary variable equals my array I. No, my array 0. And then my array, my slot equals temp. No, my array 0. Let me make sure I do this right. My slot is going to equal my array 0, which is going to be temp. There we go. And then in between there, my array 0 is equal to my array, my slot. So I'm making a temporary variable, holding my first value, setting my first value equal to my lowest value, and then setting the location where my lowest value was equal to the temporary value. And then we're familiar with the idea that we are just going to draw the array, right? Copy this and paste it down here. So what we should get here, all I've done here is drawn the array. What we should get is our bubble sort working, a bunch of rows of hyphens for me. We should get our selection sort, should tell what the number is and what the location is. And then we should get another array where these values have been sorted. So in this case, the 4 would be in the front and the 34 would be in slot 5. We'll see what happens. Bubble sort's working. We love it. Selection sort is there. Our numbers are 76, 45, 84, 78, 49. 7 is our lowest number, and it is in the 8th slot, which is what is represented here in these first 2 digits. It swapped the 7, and the 76. So now 76 is in the 8th slot, and 7 is here in the 1st slot. That's what the insertion sort does, but it's going to do it 10 times until we have the right order. I need to put in some new lines here. So 20 is my lowest number. It's in the 8th slot. I'm swapping the 70 and the 20, which is what happened here. Now I want to do this again and 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 again, right? So I need to have this all inside of a nested for loop. So I'm going to tab it all over. Gonna have to reset my small and my slot every time. So my first for loop is going to start before I declare my small and my slot. And because I've already used I, I'm going to start with J, which is not best practice, but it does work. and all the way down to where I actually swap the values. And then it's going to run the loop again. Now, the first time it goes through the loop, my I is starting at 0 and going all the way up to 10. But I don't want it to start at 0 every time, because the second time I goes through the loop, I want it to start at 1. So the thing we can do here is just start I at J. So as J goes up, the number of iterations that it goes through the I actually goes down. So now if we run it, theoretically, we had 29 in the 8 slot, we swapped it. Eventually had 46 in the 2 slot, we swapped them. 29 went into the 2 slot, we swapped them. 59, it looks like it's just bouncing back and forth now. So we did not do it correctly. Somehow 29 got all the way to the end. It should not have been at the end. 29 should have been at the front. The code is wrong. So effectively, I guess this is the selection sort. Now you could write the selection sort by finding the largest value instead of the smallest value. You would just be changing the direction you move it. To make it faster, a faster sort is you could go through and find the smallest value and the largest value in the same loop and move those to the polarized ends, right? And then you would run half as many loops. So that would be faster.